Welcome to another RDWorks Learning Lab. It's nice and quiet in here at the moment because it's been a very hot day outside, and I've run the machine to what I use as my limit, 30 degrees C. I've got several apologies to make to start with. First of all, I apologise because I haven't jumped back onto our acrylic fest. I've been distracted onto other things. And a second apology goes to Mike Henry, who very kindly sent me something which we could have touched on the session that I'm going to currently do. Something that I can't get here in the UK, but it's something that will allow me, hopefully, to get 0.05 dots down successfully, nice and black. These are special heat-sensitive tiles with a heat-sensitive surface. Now, as I said, I can't get these in the UK, and Mike Henry kindly sent me some. So they're going to be used in a future session when we will try and find out that we can truly get probably 500 dots per inch. This would link in very nicely with my search for the 1000 DPI dot saga that we've been chasing, the claim that's been made by Thunder Laser. Now, it just so happens that Mike, who sent me these, has got a Thunder Laser machine. Now, 3 or 4 weeks ago, I did something that I rarely do, and that's look at somebody else's information and videos. I was interested in whether or not Thunder Laser actually tell me how they get 1000 DPI pictures. Sure enough, there is a video posted up there. It's not quite telling me the whole story, but it's told me enough to make me smile. So what I'm going to do in this session is start off by working through the method that Thunder Laser are using. So let's jump to RDWorks and see how you can perform this magic for yourself. But let's just take a look at this little picture that I've loaded in here. It's quite a difficult picture to work with because there's not a great deal of contrast in it. We've got some hairs coming up, this grey round here, and if we take a look in the background, the bed that he's got his head hanging over the edge of his dog bed has got like a corded effect, and so we get these strange patterns that may crop up when we start working with this picture. Now, to get the bitmap handle on, I need to click on the picture to put handles around it, and then I can bring the bitmap handle into play. Now, why it's doing that, I've got no idea. It's the first time I've used it, but hey, there we are. We've got our bitmap handle available to us. Now, we look up here and we find that we've got a resolution of 372, and I must point this out to you, pixels per inch. Now, there is a big difference between pixels per inch and dots per inch. A dot is something that we can create with the laser machine. A pixel is a square block that appears on a computer screen. Now, I'm just going to gently tease this picture up just a little bit in terms of brightness and in terms of contrast. Let's just see what happens. There we go. Just make it a little bit more vibrant. We've just spoken about dots. From our previous work, if you're using a 2-inch lens or even a 1.5-inch lens, you're going to be struggling to produce a burn on paper, on wood, on card, on leather that is better than 0.2 of a millimeter diameter. And therefore, if you want dots that sit against each other like the pixels do on the screen, pixels don't overlap, therefore your dots should not overlap. Thus, if we set the resolution of the screen to 127, we'll find that 127, if you do the calculations, 25.4 divided by 127, that will come out to a dimension of 0.2. Now that's 0.2 of a millimeter, which is our dot size. So that's the best resolution picture that we can actually produce. That's not very impressive, I hear you say. But those are the laws that we have to work with.
Yeah, you can just about see the pixelation in the background here now. Look, we'll leave it at grayscale and we'll change the resolution at the moment by just saying apply to view. And we'll see whether those pixels change size. And there we go, they have changed size now. And up here we've got our resolution of 127 pixels per inch. So now our pixels basically match our dot size that we can produce. But of course we can't produce all these different colours. We can only produce a dot that is either black or nothing. So what we're going to have to do is choose dot graphic. And we can apply that again. And now what we've got is something that we didn't have in previous versions of RDWorks. We have a nice clean black and white dot image. Here it is. Okay, so let's just look in at something in particular. And we shall find that what we've got is a series of different density black dots. Sometimes the dots are not black, and what we've got is black lines. Right, we'll zoom right in now, and what we can see here, for example, where my arrow is, we've got a dot, a white space, a dot, a white space, and then we've got two dots and two white spaces. Now the way that the tube will respond to this, or the power supply will respond to this, as instructions from the controller will go down like this. It will say turn the tube on for this black pixel, now turn it off. In other words, where it sees a line, it only turns on at the beginning and turns off when it gets to white. So that's an important thing to remember. Dots with spaces between turn the tube on and off. Joined up sets of dots keep the tube on between the first and the last pixel. And what we're trying to do, we're trying to match every one of those dots or pixels with a burn from the laser tube. Now I think it's pretty obvious, you can see that these pixels are square. So I have got no control over what happens with my X scan. If I had alternate pixels, then the tube would be going on, off, all the way across a scan line. But because the pixels are square, not only do I get 127 pixels resolution across the page, I must also set the scan lines to 127 pixels per inch down the page as well. Otherwise I should get some strange aliasing patterns. Okay, so it's quite important that you remember that fact as well. Okay, well that's enough of our review of dots as we know them. Let's take a look at some of the magic that Thunder Laser are using to get to their 1000 resolution pictures. And this time we'll set our output resolution. This time everybody's happy now. We're going to have 1000 pixels per inch picture. Note I say pixels per inch, not dots per inch. We're now going to go and dither, and we're going to use net graphic, and we've got a frequency of lines per inch, which I will explain to you in a few moments. We're going to set that at the moment to about 10, and now we're going to apply to view. You're impressed, aren't you? Does that look like 1000 DPI picture to you? Well, there's a good reason why it's not. If we look round the edge of these blobs that we've produced here, and I'm going to be rude and call them blobs, what we shall find is there's all sorts of little pixelation around the edge of them. Look, those are the 1000 pixels per inch. We've produced blobs out of the 1000 resolution pixels. And I can demonstrate that because if I change that resolution down to say 100, they are now 100 pixel per inch blobs as opposed to 1500. And there we are, there's 1500 pixels per inch blobs. Still not very impressive, is it? So okay, let's change this thing here, the frequency, the lines per inch, and let's take that up to about 70. Wow, that looks a lot better, doesn't it? Let's go and have a little bit of a closer look at it, shall we? we've got something there that we can't actually produce. When we come to burn it, we can't burn various size dots. We can only burn one size dot because we've only got one constant power that we're using. The dot graphic approach put the same size dots at different densities. This is a completely different approach, and technically what we're trying to do here, and let's zoom in and let me change this back to a lower resolution so that I can show you. 100, say, pixels per inch. If we have got dots at 100 pixels per inch like we have across here, then what we should be doing is burning lines, a lot more black lines in the picture than when we do a dot picture. So that cross there, for example, should be made up of one scan line going across that leaves a white pixel, then the next scan line coming back will stop there and leave 3 white pixels. This is a much easier style pattern for the laser tube to burn because it's much more little lines rather than single dots. We've got single dots here, but that's only because we've got a very coarse resolution. As soon as I start putting this resolution up to say 500, that we get a lot more black lines, which are the burn lines, and even where we get white areas, lots of white areas, like down here, we're still not attempting to burn single pixels. We're burning blocks of pixels, lines in other words. There are the odd single pixel around, and if they were missing, it wouldn't make a great deal of difference to the pattern. The magic that Thunder Laser are using is not really magic at all. They're cheating. So here we are. We've got the resolution set to 1500 pixels per inch. This picture is a picture made up of blobs, which in turn are blobs of 1500 pixels per inch. So we cannot copy those blobs. We can't copy each one of those blobs because we don't have the capability with our dots to get to that resolution. The best that we can copy would be 127 pixels per inch, because the most that we can produce with our machine is 127 dots per inch. I hear you say, but Thunder Laser can do it because they have got a rather special lens system that you can buy, a rather expensive lens system that you can buy. Now what we're seeing there with those strange patterns on the screen is the aliasing effect between the pixels that are on the screen and the pattern that's in this image, because if I zoom in you can see the pattern clearly, and if I zoom out you get interference between the pattern at various degrees of resolution on the screen. Well, I'm just going to take the liberty of showing you what's on the Thunder Laser website. Here are the 3 types of lenses that they show you are available for their machine. So if we go to the Parallax Technology website, we'll find this little table here, which is a very neat summary of the spot sizes for all the standard focal length lenses that you can get. Now if we take a look here at the 2-inch focal length lens, it is 0.004 inches, which is actually 0.1 millimeters diameter. So here we are, 0.1 of a millimeter, which tells me that this standard laser head that they're using is a 2-inch focal length lens. Now I defy anybody to produce 500 dots per inch with that lens. The most you'll be able to get is probably close to 127 to 150 dots per inch. It's just physically not possible to damage the material to that fine resolution. So that's problem number 1. Problem number 2 is this high resolution head here with a 0.05 claimed dot size. It says it can engrave photos up to 1,000 dots per inch. That may well be the theoretical size of the dot, but even if that is the theoretical size of the dot at 0.05, if you put 0.05 dots side by side as pixels are on the screen, you will only get 500 of those per inch, not 1,000 per inch. So we've just got a total mishmash of facts here. Okay, now this is where Thunder Laser dump you. You've got a picture with blobs in it. The blobs are made up at a resolution of 1500 pixels per inch. But how do we go about burning this picture? And that's what we're going to investigate next. We're going to jump into virgin territory and find out, is this a nice easy way of producing pictures or not?
Again, please excuse my rather crude little picture, but this is going to serve to explain how that net graphic works. I said I would explain to you what the lines per inch means. Well, the lines per inch is the spacing between the blobs. It doesn't work quite like you think, in that we put a blob here, a blob here, and a blob here, and then the next blobs go here, like this. Okay. Now, they're not all black blobs, but that's basically how the pattern of blobs are arranged, and they either are white blobs or black blobs, depending on the density of the picture that's trying to be portrayed. You'll see that we've got lines of blobs that run across, and they run across the way that we scan, i.e. like this. Whereas the pattern is arranged at 45 degrees. As I said, we're getting the benefit of a long line, not just a single dot that we're trying to produce. So we're drawing many more lines on this pattern than we are dots. That would be true if we were running within the resolution of our capability. And remember what our capability is. Our capability is 0.2 dot millimeters, which is a resolution of actually 127 PPI when it's on the screen, and DPI when it's down being burnt. So the problem is, how do we sort out the increment that we're going to burn this pattern at? Well, the first thing we can do is just guess. Theoretically, we shouldn't. We ought to try and be logical about it, and we'll come back to this logical approach in a few moments' time, because I have to admit that when I started this work off a couple of days ago, I didn't think of doing this. I just dived in. For a 2-inch lens, I've got a 0.2 dot size. So therefore I shall have a line that is approximately 0.2 wide when I scan across here. So I don't want my lines to overlap because I don't want overburning. So therefore, if I make my increment 0.2, then my lines will sit nicely against each other. Now that was based on the theory that I don't want my pattern to overburn. It didn't take into account any relationship between the scan lines themselves and the, if you like, the frequency of this pattern. So here's my first attempt. I was running at 500 millimeters a second, which I think this machine can do. I set the power quite high to 45%, and I changed the increment for line spacing to 0.18, because although I'm using a 2-inch focal length lens where I don't stand much chance of getting a 0.2 dot, I think I stand a pretty good chance of getting less than 0.2 for a line, because as I run faster and faster, the lines get thinner. Now we've seen that demonstration, so we know that to be a fact. And I was using the standard settings that you saw me demonstrate, 1500 pixels per inch, a grid spacing basically of 70 lines per inch. And here was the result. From where you're looking, it might seem to be quite a reasonable picture. From where I'm sitting, it's rather overburnt. Look, if I go into this dark area here or any other dark area, I should be able to change its colour by just scraping it very slightly. And that's because I'm scraping off the burn that's on the surface. That means that I'm basically producing a 3D picture, which I can feel. Not good. Maybe I can go for an even thinner line spacing with a 1.5 inch lens. I still kept the line pitch at 0.18, but maybe my guess here was wrong. Because I've got overburning, my lines must actually be overlapping. And so by going for a 1.5 inch lens, I would naturally produce a thinner line, and leaving all other factors exactly the same, what result do we get? Well, we're still getting some overburning here in these dense areas. It's not quite as bad, and it's not quite as 3D because I haven't got quite as much overburning. So in principle, I'm going in the right direction. So then I said, okay, let's really take a quantum leap now, and let's go to my special compound lens, because with my compound lens, I know that I will get 0.1 line thicknesses. So here we are. I've got 0.1 I've chosen as my increment. Still exactly the same picture settings, but I changed the speed down to 200 millimeters a second and the power to 30/30. Rubbish, isn't it? So I stayed with my compound lens because, you know, parts of this were okay. So maybe I made the wrong choice there. I've still got my increment set to 0.1, but this time what I've done, I've pushed the speed right back up to 500 millimeters a second with parameters that we had before, 45% power. Same old numbers over here, 1570. And yeah, it's still a dark picture and not good. So back to the drawing board, and this time I produced a picture which was 90 lines per inch and 300 millimeters a second, 0.15 increment this time with my compound lens. Yeah, it's not terrible. There's not much overburning there, but a bit. But hey, something else appears to be happening here. We're getting lines going across the picture. Can you see that? So at this point, I stopped and thought, hang on, there's got to be a logical approach to how to decide upon the scan line. So after several hours of burning pictures and not getting very far, I came back to this basic concept here and said to myself, well, a certain number of lines per inch this way, but by the time it's converted into this direction, we've got a different resolution for the line pitch. So it's not, let's just take an example, the one that we've been using. Let's assume that we're going to use this number of 90 lines per inch LPI. So we've got 1 inch, which is 25.4, because our lines per inch is the unit, but 1 inch is 25.4, and our increment comes out as millimeters. So we need to work in millimeters. So 25.4, which is 1 inch, divide that by 90, equals, so the line pitch up here is 0.28. But of course, that's not the same as the line pitch here, because this is like a 45-degree triangle here, as you can see, where 1 inch is the hypotenuse, but we're actually scanning along the opposite side. And if you do the maths, you'll find that it comes out at 17.96 millimeters instead of 25.4. So in reality, our scanning interval down here is actually 17.96 divided by 90, which is 0.199. Now, that's not a number
that I chose accidentally. I chose 90 lines per inch because I knew that it would come out to 0.2. Now 0.2, wow, that's the thickness of our line, very likely, especially if we put a 2-inch lens in. But I'm not going to put a 2-inch lens in. I'm actually going to keep my my compound lens in at the moment. And the worst scenario is that I'm going to get white between my burn lines. So now that we've got a logical approach to setting the increment, the line interval, I went in with high hopes. You're impressed, aren't you? I mean, all these parameters are the same as they have been before, except we're using lines per inch 90. We're using the compound lens, but I'm using an increment of 0.2. Something wrong with the machine, there must be. Tell you what we do. Let's change that increment. Because we're using the compound lens, what we can do, we can change this to 0.1. I think we've got a fairly serious aliasing effect here. This is the scanning interval running across and trying to make a decision about a huge number of pixels that are buried underneath this line. And it's getting very, very confused. What I'm really saying is here, Thunder Laser didn't show you how to use this 1500 pixels per inch. In the real world, they stopped short of that and just told us how to use it on the screen. You wonder whether or not there's something wrong with the machine or the lens when you see a picture like this. So what I did was to take exactly the same settings, 30% power, 0.1 increment, 300 millimeters a second, with a compound lens, and this time I went back and did a straight dot dither. 0.1 is equivalent to 254 dots per inch, so I set my picture to 254 pixels per inch. And here's the end result. Now it's still not particularly good because look, we've still got overburning taking place there. These were not realistic numbers for engraving on paper. It's just that I used them to compare these two approaches. As you can see, the density of the picture is about the same, but we don't get any aliasing this time because we're using 0.1 to match the pixel resolution. With a slightly more conservative approach, much more what we've learnt about before, I backed the power off to 15% and the speed put down to 200 millimeters a second. We still got our 0.1 increment with a compound lens, and we're still using 254 dots per inch, which is the correct resolution for everything. And here was our end result. And again, we've got just the merest amount of overburning here, but it come out a little bit washed out. I haven't spent a great deal of time setting this up. I just was throwing this together. But I think you can clearly see that dots appear to be a much more predictable and reliable system than net graphics. Net graphics looks good on the screen and you can claim all sorts of super resolutions for it, but when it comes to putting dots down on the real world, we've got some problems. Now, in the text that accompanies this video, I'm going to add the Thunder Laser video link so you can go and watch it yourself. The video is all in Chinese, but there are subtitles across the bottom. They keep using little phrases like "our experience shows us," "we have seen from tests." Basically, they've not analysed this, I don't think. They are just, much like I was, shooting in the dark. Well, I'm very confident that I'm not going to be chasing the 1000 dot picture anymore. I might be looking to get to 500 with those thermal tiles, and if I can, that will be brilliant. But we've already seen that we can get pretty good quality pictures out of 254 pixel per inch resolution pictures.
that convert to 254 dot per inch pictures. So we're making our pixels and our dots match, and Thunder Laser are not. They're claiming one thing and doing another. So thank you very much for your time, and I shall see you in the next session.